Welcome to Breezy Sleepy Science. I'm so happy you've joined us for this peaceful journey. Maybe your day has been long, or perhaps you simply find comfort in drifting off while contemplating the stars instead of counting sheep. However you arrived, this space is for you. Let your body settle into rest, your breathing soften its pace, and your thoughts grow light, as if the universe itself were cradling you. Tonight, we explore cosmology, the magnificent story of everything that exists. From the first spark of existence to the birth of colossal galaxies, it's a narrative of immense scale, profound mystery, and endless wonder. Some of what you hear might surprise you, or simply stir a gentle curiosity as you float toward sleep. If these serene explorations bring you calm, feel free to like this video and subscribe to the channel. It helps other quiet travelers find their way here. But for now, let's begin.
In the universe's earliest moments, light was so incredibly dense, it behaved as if it were solid matter. Right after the beginning, the cosmos wasn't dark or empty, it was radiant. Photons, the fundamental particles of light, were packed together so tightly they couldn't travel freely. They constantly bounced off one another and off particles of matter. This thick sea of light generated real pressure, almost as if illumination itself had substance, weight, and texture. Over eons, as the universe expanded and cooled, these photons finally broke free, streaming outward to become what we now detect as the cosmic microwave background, the faint, ancient glow that still permeates all of space. That subtle radiation is the stretched-out remnant of a time when the universe was so brilliant that light itself acted like physical material. According to some theoretical models, the process of cosmic inflation might still be happening in distant regions, forever separated from our view. Cosmic inflation is the concept that in its first infinitesimal moment, the universe expanded faster than light. Some models suggest this inflationary process didn't stop everywhere simultaneously. Instead, it may continue eternally in far-off pockets of reality, constantly generating new regions of space-time. These inflating domains would swell so rapidly that no light signal could ever cross the void between them and us. In this view, our entire observable universe is just one bubble in a vast cosmic foam, with each bubble sealed off from the others by the relentless stretching of space. We can never observe those other regions, never interact with them, yet they might exist, endlessly budding into the emptiness. To consider that our entire cosmic neighborhood might be just one finite flower on an infinite tree is both humbling and strangely beautiful. Black holes might carry within them imprints from the universe's very first instance. We typically think of black holes as the graves of massive stars, but some could be older than any star. Cosmologists propose the existence of primordial black holes, formed in the turbulent chaos of the universe's infancy. If density variations in that initial fiery second were powerful enough, entire sections of space could have collapsed under their own gravity before atoms, stars, or galaxies ever came to be. Such black holes would carry clues about the conditions immediately following the beginning. They could range from the size of mountains to the mass of stars, hidden throughout the cosmos like ancient relics of creation itself. If discovered, they would be cosmic time capsules, safeguarding secrets from a universe younger than a single heartbeat, from an era when the rules of physics might have been different from those we know today. We are stardust dreaming of the stars. Near the beginning of time, the flow of time itself may have been different from our current experience. Time feels constant to us, each second ticking by evenly, one after another. But near the cosmic origin, things might not have been so straightforward. Einstein's theory of general relativity tells us that time and space are intertwined, and their behavior depends on energy and gravity. In the incredible furnace of the early universe, densities and energies were beyond comprehension. Time itself may have stretched, warped, or moved more slowly compared to our present flow. Some theories even propose that what we call the start of time may not have been the true beginning, but rather a transition from one state of existence to another. When we gaze back across billions of years, we might not just be looking through space, but also across evolving rivers of time itself. The largest known structure in the cosmos is a billion-light-year-long wave of galaxies. The universe isn't uniform. Galaxies aren't scattered randomly like dust. They form immense patterns, threads, walls, and filaments. One of the most spectacular of these is the Boss Great Wall, discovered through extensive galaxy surveys. It's a sprawling chain of superclusters extending nearly 1 billion light-years. Within it, galaxies are strung together like luminous beads on invisible strings of dark matter. To grasp its scale, if our Milky Way were a single dot on a map, this wall would stretch across entire pages. These colossal structures remind us that the cosmos is not only vast, but also deeply patterned, a form of architecture on the most grand stage imaginable. Neutrinos generated during the first second of creation are still passing through your body at this very moment. Neutrinos are ghostly, nearly massless particles that rarely interact with normal matter. Trillions of them stream through you every second, completely unnoticed. Many are produced in the sun or distant stars, but some are unimaginably ancient. Within the first second after the beginning, neutrinos flooded the universe. Unlike photons, they slipped free very early because they interact so weakly. They have been traveling through space ever since, forming what physicists call the cosmic neutrino background. Though nearly impossible to detect directly, they are everywhere, including within you right now. Each one is a relic from the universe's very first heartbeat, still whispering its way through the cosmos almost 14 billion years later. Entire galaxies appear to be moving due to the gravitational pull of hidden masses beyond the edge of our observable universe. Astronomers have noticed that some galaxies aren't drifting in the directions we would predict. Instead, they seem to be tugged by an unseen influence, something lying far beyond the part of the cosmos we can see. This motion has been nicknamed dark flow. It might be caused by enormous masses outside our cosmic horizon, invisible yet powerful enough to bend the paths of whole galaxy clusters. We cannot observe these hidden regions directly, but we see their gravitational fingerprints in the motions of galaxies closer to us. It is a reminder that the observable universe is just a patch of something much larger, and that unseen structures may still be shaping the cosmos we inhabit. The vacuum of space may not be empty, but simmering with quantum energy. When we picture empty space, we often imagine true nothingness, a complete void. But quantum theory suggests that even the vacuum is restless. Tiny particles flicker in and out of existence, borrowing energy from the uncertainty principle before vanishing again. This active sea is called the quantum vacuum, and it may hold the key to one of cosmology's greatest mysteries, dark energy. The accelerating expansion of the universe could be driven by the inherent energy of this seemingly empty space. In that sense, every cubic inch of apparent nothingness is alive with potential, buzzing invisibly with the physics that determines the ultimate fate of the cosmos. Patterns in the cosmic microwave background might contain ripples from before the beginning. The cosmic microwave background is the most ancient light we can observe, released when the universe was only a few 100,000 years old. To the naked eye, it looks almost perfectly uniform. But sensitive maps reveal tiny variations, ripples less than 1 part in 100,000. These patterns seeded the galaxies, stars, and planets we know today. However, some of these ripples are stranger, unusually cold, or aligned in ways that might point to physics that existed before the beginning itself. They could be scars from collisions with other universes, or echoes of exotic fields that shaped inflation. The faint patterns in this ancient light are not just random noise. They may be the fingerprints of realities far older and larger than our own. The ultimate fate of the universe might depend on particles we haven't yet discovered. The destiny of the cosmos, whether it expands forever, collapses back on itself, or drifts into heat death, depends on the nature of its most mysterious components. Dark energy drives the expansion. Dark matter shapes the galaxies. Both may be connected to particles we have never directly observed. Physicists search for these unseen particles in deep underground labs and powerful particle colliders, hoping to find the missing pieces of the cosmic puzzle. If they exist, they will tell us whether our universe is stable, whether it might someday decay, or whether it could cycle through endless rebirths. Within the smallest particles may lie the largest answers, hidden keys to the story of everything. Gravity may feel weaker than the other forces because it leaks into hidden dimensions. We think of gravity as a universal force, binding planets to stars and stars to galaxies. But compared to the other fundamental forces of nature, it is astonishingly feeble. A small refrigerator magnet can lift a paperclip against the gravitational pull of the entire Earth. Some physicists wonder if gravity feels weak because it isn't confined to our familiar 3 dimensions of space. Instead, it might spread into additional, hidden dimensions that we cannot perceive. If this is true, the force we experience would be only a faint echo of a deeper reality. These extra dimensions could be curled up, too tiny for us to notice, yet large enough to dilute gravity's strength. It's a hypothesis that could explain why the cosmos holds together the way it does, and a hint that our universe might be part of something more complex and layered than we can currently imagine. The cosmic horizon hides regions of the universe we can never visit. When we look out into the sky, we are actually gazing back in time. But there is a limit, a boundary called the cosmic horizon. Beyond this limit, light has not had enough time to reach us since the beginning. Those regions of space are real, likely filled with galaxies, but they are forever concealed from our view. The horizon isn't a physical wall, but a limit of our perspective, like standing on a shoreline and seeing only as far as the Earth's curve allows. Every year, the horizon expands slightly as light from more distant reaches finally arrives. Yet, the expansion of space itself pushes other regions even farther away, beyond our view forever. The cosmic horizon is a quiet reminder that no matter how powerful our telescopes become, there will always be more universe lying beyond, eternally out of sight. Primordial black holes could be as small as atoms or as massive as mountains. Most black holes form when massive stars collapse, but there may be older, stranger varieties, primordial black holes. Born in the first instance after the beginning, they could be wildly different from the black holes we know today. Some might be tiny, with event horizons smaller than an atom, while others could possess the mass of an entire mountain range. Over billions of years, the smallest would have evaporated through Hawking radiation, but others might still drift invisibly through the cosmos. If they exist, they could even account for some or all of the mysterious dark matter. These hidden relics would be scattered everywhere, silent fossils of creation itself, so subtle that one could pass straight through Earth unnoticed, and yet collectively powerful enough to shape the destiny of entire galaxies. The early universe may have given birth to cosmic strings stretching across the void.
Theories of high-energy physics predict that as the universe cooled from its hot, dense beginning, strange defects in space-time could have formed. Infinitely thin but immensely powerful, these are called cosmic strings. Unlike ordinary strings, they are not made of matter, but are cracks in the fabric of space-time itself, potentially stretching for billions of light years. If two cosmic strings were to cross, they could snap and release enormous bursts of gravitational waves, ringing through the universe like a struck chord. Though none have been confirmed yet, their discovery would reveal physics far beyond our current understanding. The idea that the early universe might still contain hidden filaments, invisible to our eyes but etched into the fabric of reality, is both haunting and beautiful, like scars from the cosmos's own violent birth. Ripples in space-time could be direct fossils from the universe's very first instant.
Gravitational waves are ripples in the fabric of space-time, stirred up by cataclysmic events like colliding black holes. But there may also be far older waves, born in the initial moment of the universe's existence. During the period of cosmic inflation, space-time itself may have shivered with quantum fluctuations, stretching those primordial ripples across the entire cosmos. These ancient gravitational waves would be incredibly faint, but if we could detect them, they would be direct fossils from the universe's birth. Unlike light, which only broke 300 thousands of years later, these ripples would carry us back almost to time zero. Scientists search for their signature in the delicate polarization patterns of the cosmic microwave background, hoping to hear the faintest whisper of creation's first breath. Some galaxies, including our own, appear to be racing toward a mysterious great attractor hidden in space. Our galaxy, along with many others, isn't drifting aimlessly. It is being pulled toward a specific region of space known as the Great Attractor. This hidden concentration of mass lies hundreds of millions of light-years away, shrouded behind the dense dust and stars of our own Milky Way, making it difficult to study. Galaxies across a vast volume show a shared motion, as though they are sliding down the slope of an invisible gravitational hill. The true nature of the Great Attractor remains uncertain. It might be an immense cluster of galaxies or something even larger. Whatever it is, its gravitational pull is strong enough to guide the paths of entire galaxies, including our own. We are moving toward it even now, carried along on the slow cosmic current of gravity. Dark energy might grow stronger over time, fundamentally altering the universe's destiny. Dark energy is the mysterious force responsible for the accelerated expansion of the universe. For now, it appears constant. But what if it changes? Some theoretical models suggest that dark energy could intensify over billions of years. If that happens, the expansion would accelerate more and more, eventually tearing galaxies, stars, and finally even atoms in a catastrophic event known as the Big Rip. In other scenarios, dark energy could fade away, allowing gravity to slow the expansion or even reverse it. Because dark energy constitutes the majority of the cosmos, its behavior determines everything about the future. And yet, for now, we do not know if it is constant or evolving. The entire fate of the universe may rest on the hidden nature of this invisible, dominant force. The universe is a story written in starlight. Cosmic voids, vast expanses with almost no galaxies, are themselves still expanding. Between the bright filaments of the cosmic web lie immense empty regions called voids. These can span hundreds of millions of light years and contain only a handful of isolated galaxies. Voids are not static emptiness, however. They are expanding faster than the rest of the universe as matter flows outward toward the denser regions. In a way, they are the growing hollows of the cosmos, ballooning as galaxies drift away. By studying these voids, scientists can test the nature of dark energy and the overall cosmic expansion. For now, they remain among the quietest and most lonely places in the universe, vast oceans of near-nothingness, still stretching wider as time progresses. The geometry of the universe may be ever so slightly curved. When we imagine the universe, we often picture it as flat, stretching endlessly in all directions. But geometry in cosmology is a subtle thing. Depending on its total energy and mass, the universe could be positively curved like a sphere or negatively curved like a saddle. Observations indicate it is incredibly close to flat, so close that if any curvature exists, it is too slight for our current instruments to detect with certainty. A universe with even the tiniest amount of curvature would, over unimaginable distances, bend light in ways that would eventually reveal its true shape. For now, we live in a cosmos that feels perfectly flat, but cosmologists continue to search for that faint, hidden curve that could tell us more about its ultimate size and fate. The cosmic microwave background is dotted with strange, unexplained cold spots. The cosmic microwave background, the afterglow of the beginning, is mostly smooth and uniform. Yet here and there, it contains unusual features, patches that are colder than expected. One of the largest is known simply as the cold spot, a region of the sky where the temperature of this ancient light dips strangely low. Some scientists suggest it may be caused by a massive void in that direction, which saps energy from photons as they travel through it. Others speculate it could be a fingerprint of physics beyond our known universe, perhaps even the scar from a collision with another cosmos. Whatever its cause, the cold spot remains one of the most puzzling anomalies written into the universe's oldest light. The first stars may have been hundreds of times more massive than our sun. In the quiet darkness following the beginning, the universe was without light. Then, hydrogen and helium gathered to form the very first stars. These were nothing like the stars we see today. With no heavier elements to help cool the collapsing gas clouds, they grew to enormous sizes, reaching hundreds of times the mass of our sun. Their light was intensely brilliant, blazing white-blue, and they lived fast and died young, burning through their nuclear fuel in only a few million years. These population 3 stars forged the first heavier elements, carbon, oxygen, and iron, in their cores. When they died, they scattered those elements across space, seeding the raw material for all future generations of stars, planets, and eventually life. Though none survive today, every atom of carbon in your body was likely once forged inside one of these long-vanished giants. Some of those first stars may have collapsed directly into the earliest black holes. The most massive of the first stars ended their brief lives in catastrophic collapse. Their gravity was so immense that when their fuel was exhausted, no known force could stop them from imploding. Some exploded as supernovae, leaving behind dense neutron stars, while others fell directly into black holes. These initial black holes were unique, not the remnants of ordinary stars, but the direct descendants of the universe's first cosmic fires. They may have acted as seeds, growing over billions of years into the supermassive black holes that anchor the centers of galaxies today. If this is true, then the brilliant quasars we observe at the edge of the observable universe, powered by black holes billions of times the sun's mass, may trace their lineage all the way back to those first collapsing stars, born in the dawn of time. Our Milky Way galaxy is hurtling through space at over 1 million miles per hour. Although the night sky appears tranquil, our galaxy is on a ceaseless journey. The Milky Way, along with all its stars, planets, and nebulae, drifts through the cosmic web at a velocity exceeding 1 million miles per hour. This motion is the result of combined gravitational pulls from nearby galaxies, galaxy clusters, and even vast unseen structures. To us, this motion feels imperceptible because everything in our local group moves together. However, when astronomers measure the cosmic microwave background, they can detect a faint dipole pattern, a subtle distortion caused by our galaxy's high-speed motion. It's a reminder that there is no absolute state of rest in the universe. Everything is in motion, everything flows, carried along in the great cosmic tide. Superclusters of galaxies weave a cosmic web across the observable universe. Galaxies do not exist in isolation. They gather into clusters, and those clusters in turn gather into even larger structures called superclusters. These superclusters stretch for hundreds of millions of light years, linked by filaments of galaxies and separated by vast cosmic voids. Together, they form the cosmic web, a pattern that resembles the strands of a spider's web or the interconnected neurons of a brain. Our own Milky Way resides within the Laniakea supercluster, a sprawling region containing hundreds of thousands of galaxies. When we map these immense structures, we see not chaos, but a profound elegance, gravity sculpting luminous threads across the universe, revealing a hidden order that spans billions of light years. Ancient quasars shine from less than 1 billion years after the beginning. Quasars are the brilliant beacons of the early universe. They are galaxies whose central black holes are feeding so voraciously that they outshine all the stars in their host galaxy combined. Some of the quasars we observe today come from an era less than 1 billion years after the beginning, when the cosmos was still in its youth. To shine so brightly so soon, their central black holes must have grown with astonishing speed, reaching masses of 1 billion suns in a mere fraction of cosmic history. These quasars act like cosmic lighthouses, illuminating the fog of intergalactic gas and allowing us to peer back into the reionization era, when the first galaxies and quasars filled the universe with light, carving it out of darkness. Their very existence poses deep questions. How did these black holes grow so massive so quickly? What were the initial seeds that gave rise to them? We may live within a local bubble of unusually empty space. Astronomers mapping the material between stars have discovered that our sun lies within a vast cavity, a bubble carved into the galaxy's gas. This local bubble stretches hundreds of light years across and is significantly emptier than its surroundings. It was likely created by a series of supernova explosions millions of years ago, which blew the surrounding gas and dust outward. Today, our sun and its neighboring stars drift quietly within this rarefied zone, bathed in a faint glow of hot plasma. The edges of this bubble form denser walls of gas and dust where new stars are actively being born. To think that our solar system resides inside the lingering footprint of ancient stellar explosions adds a strange and intimate dimension to our place in the cosmos. Dark matter may clump into invisible filaments that guide the formation of galaxies. When astronomers simulate the growth of the universe, they find that ordinary matter alone cannot form the large-scale structures we observe. Something unseen, dark matter, must provide an invisible scaffolding. In these simulations, dark matter clumps into filaments that stretch across space, guiding the flow of galaxies into strands and knots. Our own Milky Way likely sits within one of these invisible filaments, like a dewdrop caught on a spider's thread. We cannot see the dark matter directly, but we observe its gravitational influence sculpting the grand architecture of the universe. Without it, galaxies would fly apart, and the cosmic web would unravel into scattered fragments. Axions, if they exist, could constitute all dark matter. The true identity of dark matter remains one of science's great mysteries. One promising candidate is the axion, a hypothetical particle predicted by certain theories of quantum physics. Unlike the heavier particles once thought to explain dark matter, axions would be incredibly light, lighter even than neutrinos, but produced in such enormous numbers that collectively they could outweigh all the visible matter in the universe. Axions would interact so weakly with normal matter that they would slip through stars, planets, and even our most sensitive detectors completely unnoticed. Scientists have built specialized experiments using ultra-sensitive magnetic fields and resonant cavities, hoping to catch even a whisper of these elusive particles. If found, axions would not only solve the dark matter mystery, but also forge a deep connection between cosmology and the fundamental questions of particle physics. The laws of physics might be slightly different in other universes. Some versions of the inflationary theory predict that our universe is just one bubble in an endless multiverse. If this is true, the fundamental laws and constants of physics could vary from one bubble universe to another. In one universe, stars might never form because gravity is too weak. In another, atoms might not be stable at all. Our own universe appears fine-tuned, with its constants balanced in a very specific way that allows for galaxies, chemistry, and life to emerge. This raises a profound possibility. Perhaps we inhabit one universe among a countless number, most of which are sterile or chaotic, but ours is balanced just precisely enough for complexity to arise. Though we cannot see beyond our cosmic horizon, the idea that reality may be far broader than the laws we experience allows us to marvel at the fragile, specific conditions that make our existence here possible. cosmic inflation could have spawned an infinite multiverse. In the theory of eternal inflation, the universe expands not as a single entity, but as an endless froth of space.
Some regions stop inflating and form stable universes like our own, while other regions continue expanding forever, perpetually giving birth to new cosmic bubbles. Each of these bubbles could itself be infinite in size. Collectively, they form a multiverse without end or boundary. In this picture, our Big Bang was not the absolute beginning of everything, but simply the birth of our local cosmic region. Other universes may lie forever beyond our reach, each with its own physics, its own galaxies, and perhaps its own forms of life. It is a vision of reality so vast that even our observable cosmos, with its 2 trillion galaxies, would be just one small ripple on an endless cosmic sea. The universe underwent a dramatic transition from being opaque to transparent. For its first several 100,000 years, the universe was a dense fog of particles. Electrons and protons drifted freely, scattering photons so effectively that light could not travel in a straight line. It was a glowing, opaque plasma with no clear line of sight. Then, as the cosmos cooled further, electrons settled into orbits around protons, forming the first neutral atoms. Suddenly, the photons were released, able to stream freely across space. In that instant, the universe became transparent, and the light we now call the cosmic microwave background began its long journey across the cosmos. Every time we detect that ancient glow, we are witnessing the moment the universe first let its light go free, a timeless afterimage of the cosmos lifting its primordial veil. The reionization era lit up the universe with the light from the first galaxies. After the universe became transparent, it entered a dark age, filled only with neutral hydrogen gas. For hundreds of millions of years, there were no stars to shine. Then, gradually, the first galaxies ignited. Their newborn stars and powerful quasars flooded space with ultraviolet light, which was energetic enough to break hydrogen atoms back into their constituent electrons and protons. This period is called the reionization era, when the cosmic fog was lifted once more, not by cooling, but by being pierced and ionized by brilliant light. Reionization carved great, growing bubbles of transparency around the first galaxies and quasars until, eventually, the entire universe was reionized and illuminated from within. When we observe the most distant galaxies and quasars, we are catching glimpses of that pivotal moment when cosmic darkness gave way to dawn and the universe became filled with its own internal light. The cosmic neutrino background has never been directly observed. We are familiar with the cosmic microwave background, the light released when the universe became transparent. But even before that, another cosmic background formed, a sea of neutrinos released just 1 second after the beginning. These ghostly particles still stream through space today, forming the cosmic neutrino background. Unlike photons, which were trapped for hundreds of thousands of years, neutrinos escaped almost instantly, carrying information from the universe's earliest moments. However, because they interact with matter so weakly, we have never directly detected this background. They flow through planets, stars, and our bodies almost without a trace. Instruments capable of catching even a faint hint of this neutrino sea are still in the realm of future possibility. If one day detected, this background would open a hidden window into the very first second of existence itself.
The most energetic particles in the universe likely originate from beyond our galaxy. Cosmic rays are high-energy particles that constantly rain down on Earth, striking our atmosphere and creating cascades of secondary particles. Most come from sources within our Milky Way, such as exploding stars. But some cosmic rays carry energy so extreme that no known process in our galaxy could have possibly produced them. These ultra-high energy cosmic rays must come from far beyond our galactic home, perhaps from the relativistic jets of distant quasars or from violent collisions between entire galaxy clusters. Each of these particles travels for millions or even billions of years until, by sheer chance, it encounters Earth's atmosphere. When it strikes, it unleashes a brief shower of particles, a momentary firework of invisible origin. Even now, we don't fully understand what cosmic accelerators can launch the most powerful particles in the universe, only that they come from somewhere far, far away. Black hole mergers may occur frequently enough to reshape their host galaxies. Black holes are not always solitary objects. In galaxies where stars interact and clusters merge, black holes can be drawn into binary pairs. Over time, they spiral closer together, radiating energy in the form of gravitational waves until they finally coalesce into a single, larger black hole. Each such collision releases a tremendous burst of ripples in space-time. Over billions of years, these repeated mergers may be responsible for growing the supermassive black holes that reside at the centers of galaxies to their enormous sizes. When these mergers happen, the energy released can dramatically affect the flow of gas within the galaxy, either shutting down star formation or triggering new waves of stellar birth, thereby influencing the galaxy's overall structure and evolution. In this way, black hole mergers are not just rare cosmic fireworks, they are an integral part of the ongoing, quiet architecture of the cosmos, actively chiseling galaxies into the diverse shapes we observe today. Gravitational waves carry the whispers of ancient violent collisions. Predicted by Einstein a century ago, we have now finally begun to hear them. Gravitational waves are ripples in the fabric of space-time, created when massive, compact objects like black holes or neutron stars spiral into each other and collide. As they pass through space, they stretch and squeeze it, albeit by an amount less than the width of a proton. With advanced detectors like LIGO and Virgo, scientists have recorded dozens of these events, distant cataclysms that occurred billions of light years away, their faint whispers only now reaching us across cosmic time. Each wave carries a unique signature, telling us about the masses, spins, and final dance of the objects that created it. And someday, if we can detect even fainter signals, we may hear the collective background hum of gravitational waves from the earliest universe, echoes of creation itself still rolling through the fabric of space-time. The speed of the universe's expansion has changed more than once. The universe does not expand at a constant rate. In its first fractions of a second, a period known as inflation drove an almost unimaginably rapid expansion, faster than the speed of light. After inflation ended, gravity began to slow the expansion down, as the mutual attraction of all matter worked against the outward momentum. For billions of years, galaxies drifted apart at a gradually decelerating pace. But in the last several billion years, the expansion has begun to speed up again, now pushed by the mysterious influence of dark energy. This shifting pace tells us that the cosmos has passed through distinct phases, each governed by the changing balance of forces and energies within it. From rapid inflation to slow deceleration to the current acceleration, the rhythm of cosmic expansion is like a heartbeat that has changed over time, and it continues to beat into an unknown future. Some of the first stars may have formed directly from collapsing dark matter. Ordinary stars form from the gravitational collapse of clouds of gas, but some theories propose a stranger origin story for a hypothetical class of objects called dark stars. In the early universe, dark matter may have clumped together so densely that particles of dark matter annihilated upon contact, releasing bursts of energy. Instead of collapsing fully under gravity, these dark matter clumps could have inflated into giant puffy stars powered not by nuclear fusion, but by dark matter annihilation itself. They might have been incredibly massive, glowing with a faint internal heat. But unlike ordinary stars, their light would have been very different and difficult for us to detect. If such stars ever existed, they could have been the first beacons in the cosmos, later collapsing to form the black holes that seeded the earliest galaxies. Though still entirely hypothetical, the idea of stars born from the universe's invisible matter offers a haunting glimpse of what might have been possible in the cosmic dawn. The cosmic microwave background is slightly lopsided. When we map the cosmic microwave background, the afterglow of the beginning, we find it is almost perfectly uniform. Almost, but not quite. There is a slight asymmetry, a lopsidedness, with one hemisphere of the sky showing slightly stronger temperature fluctuations than the other. This imbalance is puzzling because our standard models of the early universe suggest it should have been nearly identical in all directions. Some explanations propose it is simply a statistical fluke. Others suggest deeper causes, such as new physics from the inflationary epoch, or even gravitational influences from regions beyond our observable universe. Though subtle, this lopsidedness challenges our fundamental assumption that the cosmos is perfectly isotropic on the largest scales, and it keeps cosmologists searching for the hidden story behind this ancient light. A mysterious axis of evil seems to align large-scale structures across the sky. Among the patterns in the cosmic microwave background, scientists have noticed something unusual. Certain large-scale features appear to be aligned along a preferred direction or axis in the sky. This alignment, playfully nicknamed the axis of evil, shouldn't exist if the universe is truly random and uniform at the largest scales. Even more puzzling, some of the largest cosmic structures, like the distribution of galaxies themselves, seem to follow this same preferred orientation. Whether this is a mere coincidence, a statistical anomaly, or a sign of unknown physics, no one yet knows. The name may be whimsical, but the mystery is serious. Why should the universe, so vast and ancient, show any preference for a particular direction at all? The fine-tuning of cosmic constants is what allows galaxies to exist in the first place. The universe is balanced on a razor's edge. The strength of gravity, the charge of an electron, the mass of fundamental particles. If any of these values were even slightly different, the cosmos would be unrecognizable. Stars might never ignite, atoms might never form, or galaxies might collapse too quickly to allow for the development of life. This delicate balance is known as the fine-tuning problem, and it fascinates cosmologists because it seems improbably precise. Some see it as a mystery to be explained by deeper, yet-to-be-discovered laws of physics. Others suggest the multiverse as a solution. A vast ensemble of universes exist, each with different physical constants, and we simply inhabit one of the rare universes where the constants happen to allow for observers. Whatever the ultimate explanation, it is a humbling realization that the entire visible universe, from the largest galaxy to the very breath in your lungs, depends on the exquisitely delicate tuning of invisible constants written into the fundamental fabric of reality. Some physicists seriously entertain the idea that the universe is a hologram. It sounds like science fiction, but the holographic principle is a legitimate concept in theoretical physics. It suggests that all the information describing our three-dimensional universe, stars, galaxies, even ourselves, might be encoded on a distant two-dimensional surface. Just as a flat hologram can project a three-dimensional image, the cosmos we experience might be a projection from information stored on a cosmic boundary. This strange idea originates from the study of black holes, where information appears to be stored on the event horizon rather than within the volume. If true for black holes, it might be true for the entire universe. The holographic principle doesn't mean reality is an illusion, but rather that space and time themselves may be emergent properties, shadows of a deeper, more fundamental layer of physics based on information. Quantum fluctuations may have seeded every single star and planet we see. On the smallest scales governed by quantum physics, reality is inherently uncertain. Particles flicker in and out of existence, and tiny energy fluctuations are a fundamental feature of the vacuum. During the period of cosmic inflation, these microscopic quantum fluctuations were stretched to astronomical sizes, becoming slight ripples in the density of the universe. Over billions of years, gravity acted on these ripples, amplifying them, drawing matter into the slightly denser regions. From those tiny seeds grew galaxies, stars, planets, and eventually life. It is a truly astonishing realization that everything we observe in the night sky, from the spiral arms of the Milky Way to the most distant galaxy clusters, may have originated from microscopic quantum jitters amplified by the vast machinery of cosmic expansion. The entire universe, in a very real sense, rests upon the chance tremors of the quantum world. Cosmic inflation could have created baby universes that we will never be able to observe. Inflation is the theory that the universe underwent a period of faster-than-light expansion in its first instant. But some versions of this theory suggest it didn't happen uniformly. While the region that became our observable universe slowed its expansion and evolved, other regions of space may have continued inflating, each forming its own separate universe. This process could happen endlessly, with baby universes budding off like bubbles in a pot of boiling water. Each one would be permanently cut off from the others by expansion so rapid that no signal, not even light, could ever cross the gap. Some of these baby universes might have laws of physics very different from our own. Others might look remarkably similar, containing their own galaxies and stars. If this is true, our observable universe is just one blossom on an infinite cosmic tree, with countless other branches forever hidden from one another, each carrying its own version of reality. There are likely more galaxies in the observable universe than grains of sand on all the beaches and deserts of Earth. The number of galaxies is almost beyond human comprehension. Early estimates suggested there were hundreds of billions. But deep field images from telescopes like Hubble revealed a far greater abundance. After careful analysis, cosmologists now estimate there are roughly 2 trillion galaxies in the observable universe. To put this into perspective, if you were to gather all the sand from every beach and every desert on our entire planet, the number of individual grains would still be less than the number of galaxies shining in the cosmos. Each of those galaxies contains billions or even trillions of stars. And around many of those stars orbit planets, moons, and perhaps, in some cases, life. The scale is so immense that the word infinite feels almost appropriate. When we gaze up at the night sky, we are seeing only the very nearest sparks in an overwhelming cosmic ocean, a mere handful of the closest neighbors in an abundance that defies imagination.
And so, our long journey through the universe draws to a quiet close. We've drifted across billions of years, from the first hot glow of plasma to the faint whispers of primordial vibrations that still echo through space. We've wondered at horizons we cannot cross, at galaxies born from ripples smaller than a whisper, and at the possibility that our cosmos is only one among many. Cosmology reminds us that we are woven into something vast, something that began long before us and will continue long after. Yet here you are, breathing softly in the present moment, carried by the same laws that guide galaxies and stars. Every heartbeat, every breath is part of that story.